right, so I wanted to do an example problem where we're not specifically talking about the Young's double slit experiment, but we're really focusing on the idea that interference is a property that waves exhibit. And so interference can happen with water waves and sound waves just like it can happen with light waves. So in this problem, we have two speakers that are emitting identical sound waves, and the wavelength of these sound waves is 2 meters. Just to be clear, the sound waves are also emitted in phase with each other. So they're exactly doing the same thing at the same time when they leave the speaker. We have an observer that is directly in front of one of the speakers, and he's 8 meters away. The speakers are a distance of 6 meters apart. Nothing is drawn to scale here clearly. But for this scenario, we want to ask the question, for the observer, what is the path difference between the two speakers till they arrive at him? And then based on that, what kind of interference is he experiencing at his location? So we actually, when we learn about interference, we learn that the path difference, really, we want to compare it to the wavelength in order to determine what kind of interference we're going to have. So the idea being that if you have two waves that are traveling to a particular location, they might only have to go, they might go different distances. Like this wave down here clearly did not have to cover as much distance as this wave up here. But notice that they both are at the same location in their oscillation. That is, they're both at a crest when they arrive. And so it might make more sense if I displace this and put this over here. But the idea is that when they arrive, they reinforce each other, and so we would have constructive interference. If we look further, we see that the difference between the path length can be shown on this, comparing these two wavelengths, and it is equal to 1 wavelength. And so we get into this idea that we can directly relate the difference in the path length from the two different sources, relate it to the wavelength. And for constructive interference, we have so if we have constructive interference, and we're going to call this difference in the path length delta L. If delta L is equal to some integer of the wavelength, where m is equal to 0, 1, 2, etc., that's when we would have constructive interference. If it's equal to some half a wavelength, then we actually have destructive interference. So that's sort of the general idea that we're approaching this problem with. So let's look at this scenario and what's the difference in the path length. I'm going to call this distance, I'm going to call this S1, and this will be S2. The difference in the path length will be S1 minus S2. Now S1 I can find by using the Pythagorean theorem because it's like a triangle, a right triangle. One side is 6, one side is 8. This is the hypotenuse, so S1 is the square root of 6 squared plus 8 squared. And then S2 is easier, it's just 8 meters. And we might have figured out that this was 10 because this does have the proportions of a 3, 4, 5 triangle. But in any case, if we don't and we have to do the calculations, it's okay, we still get an answer. And we find that the difference in the path length is 2 meters. Now what we do then is we compare that difference in the path length and see, does that equal an integer multiple of the wavelength? And actually this one's pretty straightforward. It is exactly 2 meters, it's one wavelength, so yes, they're going to interfere constructively. Yes. If it was destructive interference, it would be like a half a wavelength, 3/2 of a wavelength, 5/2 of a wavelength, etc. So let's actually write down what we would see if we had destructive interference. So we already have our condition for constructive interference. Destructive interference, we would want to compare the change in the wavelength would be like lambda over 2, 3 lambda over 2, 5 lambda over 2. It has to be some odd multiple of a half a wavelength. And so sometimes how we write this is m plus 1/2 times the wavelength, where m is equal to 0, 1, 2, etc. And so I did write down the constructive interference condition previously, and now I wanted to show you the destructive interference. Because if we had destructive interference, what that might be more like is I just really have to go down to here, and now if these two wavelengths come and arrive, one is in a trough and one is in a crest, they're going to exactly cancel each other out. And you can see that the difference in the path length corresponds to a half a wavelength here. It could be 3/2 of a wavelength, etc. It could be longer. It's just that this picture I showed only showed a half a wavelength difference. But that's how we why we are comparing the distance they have to travel to the wavelengths, because as they're traveling, the wavelengths are sort of superimposed on that distance, and that's why we can make that direct relationship. Also keep in mind that the wavelength is a distance, and so it also makes sense from that viewpoint. Now, in the next part of this problem, we simply are going to change this distance from 8 meters to 17 meters. And so now we want to see what is the situation if this guy basically, he's walked up further. Again, we have no real scale here. We're just changing that distance. We still want to look at the difference in the path length. And so this time, S1, we really do need to do the calculation because it's not a straightforward triangle. So we have 6 squared plus 17 squared. The square root of that is equal to the hypotenuse, and we're going to subtract from that S1. So this represents, this is S1, this is S2, which has changed to 17, and of course S1 changes as well. It turns out that this is 18 minus 17, so this is equal to a difference of 1 meter. And so delta L is equal to 1 meter, which is actually equal to a half a wavelength. And so this is destructive interference. And so just thinking about it, a practical viewpoint, what would be happening if the man or the observer started off 8 meters away from this speaker? When he was standing there, he would have heard the sound from the speakers. They would have been constructively interfering. As he started to walk away, the intensity of that sound is going to start to go down. And when he reaches a distance of 17 meters away, all of a sudden he hears nothing, because the sound and the waves coming from the two speakers are exactly canceling each other out. That's the destructive interference. And so I thought that seeing this in a different context might be helpful, because a lot of our problems that we have to do are actually just focused on the double slit experiment. But hope this helps.